Hi everyone. So this is a short video to help you remember how to do calculations and things from Unit 1. So it's been a while since we've done this, but I'll go over one of each of the problem types to just kind of remind everyone how all that works. If you are still confused after you watch this video, if you forgot how to do any of that, you can also go back to the Unit 1 module on my Canvas page. All of my notes are still up and available for you to watch. All of that stuff is still there. So the first part of this is just the intro to chem stuff, which is listing lab safety rules, even though this says fab safety, that should say lab. Lab safety rules, identifying the names of science equipment and what we use it for. So that should be pretty easy and go pretty quick for you. The stuff that you may need a refresher on is how to do problems like these, conversion problems and so on and so forth. So let's go over really quickly how to do those. So if you forgot, you're going to need this conversion chart when you do these problems. This should look very, very familiar to you. And if it doesn't, then that's going to be an issue, and you definitely should relook up how that works, how you're going to do all of that fun stuff. So if you forgot how to do simple conversions, the very first thing you need to do is you need to set up a T-chart. Your given number, this is going to go in your upper left-hand corners. You're going to put 0.007 liters there. You're going to put a nice placeholder one down below that. Then you are going to put the unit that you are converting to in the upper right-hand corner and the unit that you are getting rid of in the bottom right-hand corner. So now all that we need to do is we need to figure out the conversion factor from kiloliters to liters, or from liters to kiloliters, whichever one. So if you forgot how to do that, generally you are going to have a conversion factor that says for every one of your big unit, there are so many of your small units. And what I mean by that is for every 1 foot, there are 12 inches. So for every one of your big, there are X amount of your small. But we're not using feet, inches, miles, we're using the metric system. So in this case, we are going from our base unit liters. So if you forgot how to use this chart, all the base units are going to go here. And we are converting that to kiloliters. So this unit is going to look like that right here. Okay? So what these numbers mean, if you forgot, is in a kiloliter, there are 1,000 liters. So for every one of these, there's 1,000 of your base unit, right? So for every one of your big, there's 1,000 of your small. Then after that, all you have to do is multiply straight across on the top and straight across on the bottom. So we have 0.007 times 1, so that's going to give us 0.007 on the top. We have 1,000 on the bottom. Let's take a look at our units real quick to see what happens to them. So we have liters times kiloliters. So we have liters and kiloliters on the top. We just have liters on the bottom. And when you have something that's the same on the top and bottom, those things can cancel straight out. So we're left with kiloliters. And all we have to do is that simple division, okay? So at the very end, we should have 0.000007 kiloliters. You may also write this in scientific notation if you want to. So that's gonna be what most of these are. The only difference is going to be number 6 and 7. Where you're asked to convert between Celsius and Kelvin. So if you recall, the way to convert between Celsius to Kelvin is to add 273. The way to convert between Kelvin to Celsius is to subtract 273. So that should go very fast for you. Okay, moving along. In part 2, we have writing numbers in proper scientific notation. So this is going from standard form to scientific notation. So the form that you want to go for is number, point, number, times 10 to the something, to some number. So there can be more than one number after the decimal point, but you only want one number before the decimal point. So every single number to start on number 1 has a decimal point somewhere. Not all of them are written in, some of them are, some of them aren't. So for instance, here we have a decimal point that's kind of implied right there. And once again, we have a small typo, which I apologize for and we'll fix right now. So we'll just erase one of those zeros. So when I am moving that decimal point, just make it bigger, this decimal point right here, I'm going to move it over until I get this form right here, okay? So we're going to move this on over 1, 2, 3, 4, 5, 6, 7 spaces until we get the number 4.5. And since I moved it 7 spaces to the left, I'm going to have an exponent of 7. If I were to move that decimal place to the right, then my exponent would have been negative. Okay, so that's how you're going to do that. Part number 3 is the exact opposite thing. That's writing out a number in real form or in standard form. So we're going to go backwards a little bit. Now we have our number, point, number times 10 to the something, and we're going to convert that back into a number that looks a little bit more normal. Okay, so if we have a negative exponents, we are going to move that decimal place to the left. If we have a positive exponent, we are going to move that decimal place to the right. Okay, so in this case, we have a decimal place that's moving to the left because we have an exponent of -6. So what we have to do is we have to take that 2.43 and we have to take this decimal place and go 1, 2, 3, 4, 5, 6, put it in there, and fill in zeros to all those empty spaces. Our final number, which I'm going to write over to the right so it's a little bit less messy looking, is going to be 0.00000243. Again, it looks a little bit long, but that's what it is. Okay. Part 4 is using the equation density equals mass divided by volume. This is a plug and chug equation. All that you need to know is which unit is mass and which unit is volume. So if you see the unit grams, any derivation of that is going to be your mass. If you see any derivation of liters, that's going to be your volume. Okay, and if you see grams per liter or grams per milliliter or something like that, that's going to be your density. Okay, so in problem number 1, I have a glass block that has a mass of 66.7 grams and a volume of 24.1 liters. What's the density of that glass? So we use D equals M over V, and we substitute numbers. Our M and our V. How do I know that this is M? Because it says mass and it has grams as a unit. How do I know that that's my volume? Because it says volume and has a nice liters unit. So D equals 66.7 grams divided by 24.1 liters. You divide and you solve to get that numerical answer. I'm not going to solve it for you because I have no doubt that you can plug in 66.7 divided by 24.1 into a calculator all by yourself. Okay, next part, calculating percent error. Percent error is something that you may have forgotten how to do, but that's okay. So here's how we're going to deal with that. So when we write out the formula for percent error, you can see it in a couple of different ways, but they all mean the same thing. So if you're looking for percent error, you're going to take your actual value minus your theoretical value. You're going to divide all of that by your theoretical. And then you're going to take that whole thing and you're going to multiply it by 100, which again looks very, very, very complex. But basically, to sum up, it is what did you actually get? Subtract that by what you were supposed to get, divide by what you were supposed to get, and multiply that entire thing by 100. So not all that complex. So let's look at number 1 together. It says a student is required to measure the mass of a 90.6 gram beaker. The student gets a value of 53.4 grams. What's their percent error? So what they actually got was this, because what they get, you see that verb gets, so that's what they got. What they're supposed to get is this. That's your theoretical value. Another way you'll see this represented, you might see a formula called expected value. So theoretical value and expected value mean the same thing. So what you're going to do is you're going to take your 53.4, you're going to subtract the 90.6, divide all of that by 53.4, and you're going to multiply that entire thing times 100. Again, I'm not going to plug that into a calculator. You guys can all do it. But I will talk about errors that I see a lot. So a lot of people will try and do this division first and then subtract. Don't do that. A lot of people will switch these around and try and put the theoretical value first and divide by your actual. Again, don't do that. This is the correct form. Okay, part 6, determining the number of significant figures. So again, if you forgot about significant figures, which I really hope you didn't because we've been using them this whole time, how many values are actually significant? So we need to talk again about placeholder zeros and about significant zeros and non-significant zeros. These are all placeholder zeros. They are not significant. Okay? These, however, are all significant. These are not significant. These, however, are significant. And if that seems random to you, it's because it probably looks really confusing. But basically what I'm telling you is if you have a number followed by a bunch of zeros, they're not going to be significant unless there is a decimal point there. If there's a decimal point there, that makes those zeros significant. Okay? That's why the zeros in number 2 are not significant, but the zeros in number 3 are significant because of that presence of that decimal point that is absent in number 2. Same reason that number 5's zeros are significant because of this decimal point right here. Now, you may ask yourself, but Ms. Seiler, this has a decimal point and you said that those weren't significant. Yes, I did. And that is a little bit confusing, but the reason that these zeros are not significant is because an easy other way to write this number would be 9.7 times 10 to the negative 1, 2, 3, 4, 5, 6. So we don't write all those zeros in when we're converting that to scientific notation. We don't write all those zeros in when we convert number 2 to scientific notation. However, the second that you see a decimal point followed by a bunch of zeros, we would literally have to write this number 1.2000 times 10 to the something, okay? So if that helps, I hope it helps. Significant figures are very important because you will get some points marked off if you round to the incorrect number of significant figures. The only other thing I have to tell you is that all non-zeros are significant. So like all of them in number 4 would be significant. And if you had 40 or 4.503, this 0 would also be significant because it's in the middle of 2 non-zeros. Again, if you need a refresher, go back, go watch my notes PowerPoint again. This here, part 7, is about performing calculations and then rounding to the appropriate number of significant figures. So the only thing I'm really going to go over here is figuring out how many significant figures your answer should have. So looking at number 1, we see that there's 3 sig figs in this one because all 3 of those digits are significant. There's also 3 sig figs here because there's a number followed by a decimal point followed by zeros, so those are fine. So our answer should have 3 significant figures. I'm not going to plug it into a calculator. You're all capable of that. But number 4 down here, there's a bunch of sig figs here. There's 1, 2, 3, 4, 5, 6, 7 sig figs in this number, but this number only has 1 sig fig. So our answer can only have 1 sig fig. Okay, again, I'm not going to figure out the answer for you because you can absolutely do that. But that's how many sig figs that answer should have. So if you have questions, go ahead and talk to me in class. I believe that's it for the rest of this. I hope this video helps, and I will be happy to answer any other questions that you might have when I see you.